Hello, Chem 11, we're back. Our next topic is periodic trends. This is part of our matter and bonding unit. As usual, up here on the iPad, we've got our PowerPoint lecture notes. You can get those for free from our D2L site for the course. I also have a copy of our periodic table today because we're going to use that quite a bit. All right, so let's get into the periodic trends. If we look at the periodic table, there's kind of two main features that we're going to be looking at today. We're going to be looking at these horizontal rows, right? These horizontal rows across are called periods, hence the name periodic table. So each row across is a period, all right? Each column on the periodic table, each vertical column is called a group or family, all right? Now, every element in the same period has the same number of shells or orbits or energy levels. Every element in the same column, group or family, has the same number of valence electrons, all right? And they share properties. So that's what the periodic trends are kind of talking about with us, is properties. Now these properties are quantitative, all right? Quantitative means they can be measured using a number and a unit, right? The other way of describing something would be qualitative. Qualitative uses words. It also describes the object, but it doesn't use numbers or units. So if I was describing a fire truck, qualitatively, it's red, it's a solid, it's large, it's very loud, right? I've described the fire truck, but I haven't used numbers or units. Now, quantitatively, I can describe that same fire truck. It has 10 tires. It has 2,000 feet of hose. It weighs 5 tons. All of those have a number and a unit that go along with it. Our periodic trends have numbers and units that describe them. They can be measured using numbers and units. So this table, right, the crazy shape that it is, Mendeleev brought that forth, and it actually displays our periodic trends perfectly for us, right? The ones that we're going to be describing in class today are atomic radius, ionization energy, electron affinity, and electronegativity, all right? Let's start with atomic radius. Now, if I have a circle, right, atomic radius. You remember from math class, the radius of a circle is the distance from the dead center of the circle, right, if this was an atom where the nucleus would be, to the outer perimeter. That is the radius, all right? So in an atom, what that would mean is it's the distance, I'll bring it up here, it's the distance from the nucleus, which is at the dead center of the atom, to the outer perimeter of the atom. Now the outer perimeter would be the valence shell, or the outermost shell, right? So that distance is called the atomic radius. Basically, it's a measurement of the size of the atom, all right? Now, the atomic radius, as we go across the periodic table in this direction, left to right, the atomic radius is going to decrease. Now, why is it going to decrease? Well, as we go left to right, the atomic number increases, right? This means we're adding more protons. If we're adding more protons to the nucleus of the atom, that's putting on a greater attractive force to those electrons that are in those shells, especially the ones in the outer shell, right? So think about an atom. On the inside here is where I have my protons. If I add more and more protons, they're calling out to these electrons with greater and greater force. As you'll learn about in grade 9 electricity, opposite charges attract. So as I go left to right, I continue to add more positives to that nucleus, and it calls in with greater force. It attracts with greater force, because there's more of them, those electrons that are in that outer shell. So basically, the larger atoms will be here, and as we go across, they'll get progressively smaller and smaller and smaller until we reach the end. Now, and that's just what this says. Now, what happens as we go down a group or family, one of the columns? Well, the atomic radius is going to increase. The reason why it increases is that as we go down one of these groups or families, it doesn't matter which one, I can point over here or I can point to this one, what we're doing is we're adding more and more shells, right? Each horizontal row or period is a shell. So hydrogen has 1 shell, lithium has 2 shells, sodium 3. So as we go down, we're adding more shells or orbits or energy levels. All those terms are interchangeable. A shell is an orbit is an energy level is a shell. And basically that's what that explains. All right, that's pretty simple. We know that from drawing Bohr diagrams, correct? Now, here's the great part of this lecture. If you just understood atomic radius, then it makes it that much easier to understand the other 3. So here's a diagram here, very simple diagram. You can see as you go across, right, the atoms get progressively smaller. More protons in that nucleus that are attracting and pulling in those electrons on the outside. And there's another one there, showing different colored marbles. All right, ionization energy. I'm going to erase this because we'll do this for each of our periodic trends today. Ionization energy. Now, the trend of ionization energy kind of deals with ions, right? If you remember, ions were atoms that either gained electrons or lost electrons because they were battling with other atoms to try to, get their stable octet, that full valence or outer shell, right? If an ion gained electrons, it became negative and we called it an anion. If the ion lost electrons, it became positive and we called it a cation. All right? So keep that in mind as we go through this. Now, ionization energy. If I have an atom here, some random atom, there's my nucleus. Ionization energy, right? We'll just draw, for instance, beryllium here, right? This is beryllium. Ionization energy is the energy that I have to spend, or that is required, for me to remove an electron. So I'm coming in here and I'm grabbing this and I'm going to take it away, right? Yoink, I'm taking that out of here. So it's the energy required to remove an electron from a gaseous atom. Now, what does that mean? A gaseous atom means just a single atom by itself. If there was a beryllium here, beryllium's my example. You can do this with every atom. Every element has its own ionization energy values. So I'd come along here and I'd want to take out this electron and just remove it, right? Now, think about it. I've got a bunch of protons that are in here. Those protons are trying to attract this negative electron, right? Positive, negative. They want to get together. So I have to overcome the power of that nucleus, that attractive force to its own electrons, if I'm going to remove it. So I got to outwork the nucleus and pull it away. That means I'm spending energy, all right? That's what ionization energy is. So, as we go across ionization energy, what happens is it increases. Why does it increase? Well, think about the atomic radius discussion we just had. We continue to add protons as we go across any of these horizontal rows. That means there's more positive charges calling out and attracting to those negative electrons. So if I try to steal one of these negative electrons and that nucleus is jam-packed full of more protons, then it's going to be harder, right? They're all pulling in on these electrons. So the number of protons increases, which means the positive-negative attraction increases. And I got to work harder to take that electron away. As we go down a column, the ionization energy decreases. Why is that? Why does it get easier? I spend less energy. These atoms are getting bigger. Well, as I go down a column, again, I am adding more orbits or shells. Yes, the number of protons also increases, but those electrons are just put out there further and further and further. So this means that it gets easier and easier to take the electrons away. Even though there's a lot of, look at, if we look at cesium here, it has 55 protons, but it's also got 1, 2, 3, 4, 5, 6 shells. Those electrons are way out there. And even though there's a lot of protons, it's not enough to really attract those electrons with any significant force. Therefore, I can steal pretty easily from cesium. And that's kind of what this is mentioning here, right? The number of protons is increasing, and this is going to pull in on those electrons even tighter. And as we go downward, right, it gets weaker or decreases, and that's because we're adding more shells. Now, there's a thing called multiple ionization energies. We'll bring that periodic table back in just a second. We'll erase this, and we'll use our beryllium here as an example. So I'm going to blow up the beryllium here, make it bigger. And we'll number these electrons. So we'll call this electron number 1, 2, 3, and 4. So, multiple ionization energies. What this means is I get a gaseous atom, an atom all by itself, just like our beryllium here, and I want to take more than just one electron, right? If I need 8 electrons in my outer shell, maybe I want to try to take more than one here. So I get greedy. I'm going to try to take 2, 3, 4. We're going to take all 4 away from this beryllium and see what the cost, doing that business, the ionization energy value does. So here's what happens. If I take the first electron, electron number 1, the first electron is going to cost me 0.9 kilojoules per mole. Now, don't get caught up in kilojoules per mole. We'll talk about that. I know we haven't even talked about what a mole is, but it's a way of measuring energy. Think of this as dollars. It costs 90 cents. So to take this electron right here, it's going to cost me 90 cents. And I go, oh, 90 cents, that's easy. I'm taking that. All right? Now, think about what happens here. Why is it 90 cents? Well, if I get rid of the BE, I know on the inside of here, I've got 4 protons. There are neutrons in there as well, but I'm not too worried about the neutrons. In this nucleus, I've got 4 protons. And the attractive force of positives to negatives is pretty much balanced. I've got 4 electrons, 4 protons. I take that one away, and what happens? Well, that electron is gone. I paid my 90 cents. And what actually happens is the atom slightly, it sinks in just a little bit, cinches in, it becomes a little bit tighter. Why is that? Well, I still have my 4 protons, but now the attractive force of those 4 protons on the electrons is spread over only 3 electrons, not 4. So there's a slightly greater force now, 4 against the 3, pulling it in. So I say, you know what? I'm not done. I'm going to take this second electron. What will that cost me? So I go to take the second electron, yoink, and I take it away. And I find out, whoa, the price has gone up. It's 2.1. Wait, the first one's 90 cents, the second one's 2.1? Well, like we just said, when I take this electron away, the atom cinches in a little bit closer because I've still got the 4 positives pulling in, but now their exertive force is only on the 3 electrons. So this one's getting pulled in. Instead of a 1-to-1 ratio, it's now a 4-to-3 ratio, right? So there's more attractive force. And I go, okay, I'll pay that $2.10. So that's gone. I go after the third electron now. And when I say, hey, how much for that third electron? I'm going to come in here and yoink, take that away. It's 14. 14 bucks, are you kidding me? The one before was 2, why is it 14 now? Well, I just removed the second electron. What happens? Well, this second shell has nothing in it. So the second shell is gone. And now I'm trying to take electrons from the first shell. And not only that, are these electrons much closer because they're in the first shell. There's 4 protons, and their attractive force is focused on just 2 electrons, not 4, not 3, just these 2. The price goes way up when I drop a shell. So I'm digging deep in my pockets, and I go, okay, maybe I'll suck it up and I'll get the 14 bucks out. And I go, I want that last one. You know what? We started this thing, we might as well finish it. So I go after the 4th electron. Go after that. 21. Wow, the price has gone way up. Why? Well, again, this is going to cinch in a little bit when I take that third one away because all four of these now are focused on just the one electron. So now I've got to really work hard because we've dropped a shell and all of this attractive force is focused just on the one electron. The ionization energy, the cost of ripping away that electron, went up significantly again. All right? So that's how ionization energy works when there's multiple ionization energies. It gets tougher and tougher, and you have to spend more and more energy to continuously take more and more electrons. The price keeps going up as we see here. All right? So that's kind of what this says. I'm not necessarily keeping up with my swiping and my drawing. So ionization energy, here's some rows on the periodic table. We can see the general trend as it gets higher as we go over towards the, the halogens and the noble gases. There's another one that shows colors, and we can see lighter colors here, and it gets progressively darker as we go across, and it gets progressively lighter as we go down. There's one showing lines, and we can see again as we go across, each of these lines is a period on the periodic table, a row across, and it gets higher and higher as we go across. Now, electron affinity is our next one. So, electron affinity. Now this one's kind of tricky. The reason for it is the other ones tend to be, for the most part, pretty nice and neat the whole way across. Electron affinity, not as nice and neat, right? It doesn't quite follow the pattern the same way the other ones do. So what it is, it's the energy released when an electron is added to a gaseous atom. So you think, okay, wait a second, that kind of makes sense. Because the last thing, ionization energy, I had to spend energy to remove the electron, right? I had to put energy in there and spend it, right? But now if I do the opposite, instead of removing the electron, I'm adding the electron, I get energy released. That makes sense. So the trend here, now there's kind of a trend, but it's, as we'll see, it's kind of messed up a little bit as well. Overall, generally, the electron affinity increases as you go across. All right? And as you go down, it decreases. Now, I'll describe this and then we'll see that some of the elements don't quite want to follow the same pattern. So why does it increase as you go across? Well, here's kind of the hack or the cheat code for electron affinity. The smaller the atom is, oh wait, that's atomic radius, I know that. The smaller the atom is, the closer you're adding that electron to the nucleus, and so more energy is given off. All right? The closer you can get that electron that you're adding to the nucleus, the greater amount of energy. So the smaller the atom, the greater the amount of energy. Well, we know as we go across, the atoms get smaller. So we're going to get more energy given off. And as we go down, we're adding orbits or shells. So when we add an electron to something down here, we're not really adding it all that close to the nucleus. And so what happens? Very little energy is given off. Now, it sounds nice and neat, and you're thinking, okay, that makes sense. But when we look at the actual trend, look at this table. Starts out dark and then goes very light, and then gets dark in the middle, light here again. A little bit darker, and then look at nitrogen. Nitrogen's kind of odd. It should be very dark. Lots of the elements around it are dark. So overall, like I said, it kind of gets stronger as you go across, but not every step of the way. This is stronger than that. Then stronger, 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 weaker, stronger, weaker, weak, strong, 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 right? And so it kind of has these general patterns, although it doesn't follow them as neatly as the other ones do. That's kind of the point I was trying to make in my note. All right? Here's another one showing buildings, right? So if this trend was columns or buildings, you can see they start out higher and they drop. Then they go up, they drop again. They go up, they drop again. So it's not following that nice even flow. Great Pearl Jam tune, by the way, even flow. It's not following that nice even flow across or down a column like the other ones were. All right? Now, our last one. Move this out of the way. Our last trait is electronegativity. Add another 5 minutes onto the video as I spell this out. Negativity. Wow, that's a big word. Now, electronegativity. What electronegativity is, it's the relative strength of attraction that an atom has for electrons when it's in a chemical bond. So we talked about atoms and we talked about valence electrons, and we know all atoms want to get, from grade 10, we know all atoms want to get 8 outer electrons. So when I have atom A and atom B and they meet up and they want to fight for those electrons, right? There's two atoms. They're going to fight for these valence electrons. Remember, the valence electrons are on the outside here. That strength of attraction, right? This atom, atom B, is going to try to steal atom A's electrons. And atom A is going to try to steal atom B's electrons. Your strength of attraction to the other guy's electrons to try to steal them, that's electronegativity. I call it electron grabbing muscle, right? When Chemistry Fight Club starts, and the first rule of Chemistry Fight Club is don't talk about Fight Club. When Chemistry Fight Club starts, we're going to see that this atom's going to try to steal from this one, and this one's going to try to steal from that one. Who's going to be able to steal off the other guy? Well, that depends on electronegativity, your electron grabbing strength or muscle or ability. So, this is going to be a key player in bond determination. What type of bond is going to be made between these two atoms? Electronegativity is going to play a big role in that. So, as we go across left to right, electronegativity increases. Why is that? Why does it get larger, electronegativity, as we go across? Well, think about it this way. What part of B is calling on these electrons in A? It's the nucleus. All the positives are in that nucleus. So, as I go across, I'm adding more and more positives to my nucleus. And more positives are calling out on not only my electrons, but the other fella's electrons here, right? The protons in A are calling out on its own electrons, but also the electrons of B. So as we go across, we're adding more protons. We also get smaller though, right? So a smaller atom means I can get, if this is a really small atom, I can get more of my protons closer to those electrons because my radius is smaller. Smaller radius, my nucleus gets closer to there, and maybe I can convince that electron to come on over and join me, right? Now, as I go down the periodic table, what happens? Well, the electronegativity is going to decrease. So it decreases. Atoms get weaker in Chemistry Fight Club. Why is that? Well, again, I'm adding more shells. And so as I add more shells, I become larger. But size isn't a big factor here in electronegativity, right? Being a big atom doesn't make you a big electron-grabbing bully. It actually works against you because now my nucleus is way far away from your electrons. And my nucleus with my protons are calling to your electrons, but just I'm too far away because I have too many shells as I go down the column and I add more shells. Too many shells, too far away, not very strong. In terms of electronegativity, I'm kind of wimpy as I add more and more shells. All right? So that means the biggest bullies on the periodic table are over here. If we look, stronger this way and the stronger ones at the top. Our nonmetals, right? If I combine those two arrows, strong this way and strong up, it's this corner right here. That means our nonmetals are the biggest bullies on the periodic table. When it comes to fighting with other elements for electrons, these guys are the top dogs. They're the electron-grabbing bullies. And oddly as it seems, metals are the wimps. Metals don't have a very high electronegativity at all. They'll get their electrons stolen pretty easily. All right? Anyway, if we take a look at electronegativity again, you can see up here in the non-metal area, big time strength, right? The darker the box, the stronger it is, higher electronegativity. And you can see down here in the metals, not really strong at all. Non-metals, kick the butt of metals. And that seems weird because metals like iron are in steel, and steel's strong. But think of what happens to iron and other metals when they're left outside. They corrode, they rust, right? Iron turns into rust and it's flaky and weak. Why? Well, the chemical name for rust is iron oxide. Oxygen goes in there, a nonmetal, and steals electrons, right? So, there's another one showing some columns, and you can see the trend. It goes nice and easy to go across, and as you go up, right, the stronger elements end up here, same as the higher blocks are right there. Well, that's all I have for today. I hope you enjoyed the lesson and you understood everything. And if there's any questions, comments, or concerns, throw them into the comment section below this video or reach out to me through Edsby and I'll get back to you right away. Anyway, hope it made sense. Hope you understand. I'll talk to you soon. Bye-bye.